Hey, welcome back everybody. Hope you're doing well. It's snowing outside my window here in our physics lecture day. Hope things are nice and cozy where you are. Today we're going to do ropes and pulleys. Not very hard. There's just kind of one little trick as we get kind of through this, but we'll take it step by step. Make sure we go nice and slow so this doesn't get too hard. All right. You know, we use ropes to pull stuff and hang stuff and move stuff all the time. We've been practicing a little bit in our workbooks with doing rope problems. Let's let's get a little more specific and detailed about what we do. Up to now, we've pulled stuff with ropes. Let's uh, let's just draw this. Let's do a free body diagram of our object. And here's our mass. We have a force of gravity going down, and we'll call that force of gravity, which is going to equal m times g, and that also equals the weight. And then pulling up, we've got force of tension. And if this thing is just hanging there, we can tell that force of tension is going to be equal in magnitude to the force of gravity. Okay, so that gets us warmed up. Here we go. First new thing. A couple things about tension. A rope can only pull. All right, so we have a mass. A rope can only have a tension directly away from it, and it also can only pull in the direction that you're pulling the rope. It sort of makes sense, but that's actually a common mistake that kids make. In this case, if we free body diagrammed it, we would have to have some kind of acceleration. Can you see that? If I come over here and real quick, if I draw, there's my mass and force of gravity, and then my tension is going to have to go off in this direction. It's a terrible arrow. Sorry about that. There's my force of tension. Can you see that the net force can't be zero here? It's off in some direction. So we have to have an acceleration here. We can't balance with just these two forces. We can't make the net force equal to zero. So anyway, I just wanted to show you ropes can only pull, and they're always in the direction they're pointed. So let's think about tension a little more. Sam wants to pull his boat onto the shore. Now let's do something here. I'm going to change to red. Maybe that'll be a little more visible. Let's draw the forces that the rope has to deal with, and I'm going to draw a dot. We're not actually going to officially do a free body diagram, but let's think about Sam. Let's think about the rope, and let's think about the boat. So Sam is pulling on the rope, and the rope is pulling on Sam. So here's the force of tension from the rope, and here's the boat, and here's the force of tension from the rope as well. Now we've done this already, but let's stop for just a second and think about the rope itself. If we draw the rope as a dot, we have the force from the boat on the rope, and then we also have the force of Sam on the rope. And by Newton's third law, which we kind of hammered into you pretty hard, basically we've got these force pairs, these equal and opposite force pairs. Let me make a circle around them here. So these two are equal and opposite, and these two are also by Newton's third law. So what you can see is if we have all these equal and opposite to each other, if the boat's not moving, the force of right here of the boat on the rope and Sam on the rope are the same, and so we actually get to these two forces of tension are the same. All right. We've done that before. This is just a little bit of gory detail for you. So So to finish off our gory detail, this all works out if we assume our ropes have no mass. If they have no mass, then when we do our F equals MA, or our F net equals MA, if our acceleration here is is 0, okay, if this guy is 0, then I can make any acceleration and it doesn't take any force. This side has to be 0, the force is 0, and I can plug in any acceleration. So when we assume this, and it is wrong, but for our class, we're going to assume that it's right. Basically, the rope kind of just connects two objects into one, all right? And then the other thing that it means is the tension at both ends of the rope is always the same. And we've kind of done that. It's kind of made a little sense. I just wanted to give you a little bit more detail and be a little more careful about that. Let's do a problem real quick then. Two blocks are connected by a rope and sitting on a frictionless table. All right. Jill pulls on the first block with a force of 60 newtons. So here's the force of Jill, and that equals 60. Okay. What's the acceleration of the blocks? All right. So let's draw a free body diagram. Now, here's the trick. Okay. Here's the idea I really want you to be careful of. Notice what we need to do here. The system that we're accelerating is both blocks. So now, if we go up, we draw a free body diagram. Whoopsie, sorry. Got the wrong clicked thing here. There we go. And let's make the force of Jill on it. We'll put that in red for here. Okay, there's my force of Jill. All right. Now we just jump right into F equals MA, and we're off and running. I'm not going to do them as vectors because we're only doing the horizontal. So the sum of the forces equals M times A. Sum of the forces, Jill is pulling with a force of 60. Now notice I jumped a step. I didn't write the force of Jill and then went to 60. Now, here's the trick. Here's the trick. What is the mass that we're accelerating? We have to be careful here. A lot of kids like to put in 2 kilograms because that's what Jill's pulling on. That makes sense. But because we're connected with a rope, Jill is also making the 1 kilogram mass accelerate as well. So I'm going to write this a little slow. It is the mass of the two block plus the mass of the 1 kilogram block equals the acceleration. All right, very, very important. All right, I want you guys to remember this. This mass, okay, is both of these. Okay, the mass that you put in has to be both masses. So 2 plus 1 is 3. If I divide by 3, the acceleration, oopsie, I didn't make the pen go back to normal. Sorry about that. Acceleration is 30 meters per second squared. That's A. That's a terrible A. Let me fix that for you. All right. That's A. Yeah, that's a lot better. Okay, did you see how I did that? Here's the key. Remember, we have to look at the whole system, both blocks, when we do this. Okay, so that's the main message here. I want you to write in your notes somewhere nice and big. The mass has to be everything that's being accelerated. All right, so here's what I like to do. Look at this side of the equation, and the mass and the acceleration have to match. Whatever's accelerating, we have to put in that mass. Okay? Alrighty. Last thing, pulleys. This is pretty easy. Looking at pulleys, we use them quite a bit. You'll probably see this on the test. First of all, if we assume there's no friction and the pulley has no mass, we treat it just like a rope. All it's doing is changing the direction of the force that's doing the pulling. Okay, just like the rope, when it has no mass, it can have any acceleration. Same with the ropes and the pulleys together. Okay, so same idea. Basically, they're just a connection that changes direction for something. So, real quick, write these down. Go ahead and pause me and write them down. This is how we're going to solve pulley problems. Okay, now often in pulley problems, they want to know step number 5. We went all the way through step 4 in our last problem. We're just adding one more thing. Okay, and I'll show you how to do that. Write them down. I'm not going to talk about them. We're just going to do them. All right. Next, what I want you to do is copy this problem down, and I will go ahead and solve it. Okay? So copy it down, and then we'll go. All righty. So here we're off and running. Let's do black color now. No, we're going to do our forces in red. Okay, so step 1 from before. Let me make sure I do it right. Draw a picture with the forces. So I'm going to put forces right on these masses. So we have the force due to gravity of 10 kilogram block. We have the normal force for the 10 kilogram block. And then gravity is pulling down on this. Force of gravity from the 5 kilogram block. I think that's it. Okay, there's no friction, so there's nothing there. And the 5 kilogram block is not resting on anything. Now watch what I did. I did not put the tension in this. Okay, very important. I don't need to put tension in because I am going to look at the whole system together. All right, my system in this case is, whoops, let me get my dotted line out. My system is going to be all the blocks and the pulleys together. All right? So now, go back up. Number 2, straighten out the rope. This is a very important step. Okay? And let me go ahead and do that for you. What color should we have? Pictures are in black, so we'll do that as well. So there's 10 kilogram block. Now I'm straightening the rope out. Here's the 5 kilogram block. And now let's put the forces on them, or back on them. Now check out what I'm doing. There's the force of gravity from the 10. That's supposed to be straight down. And there's a normal force for the 10 kilogram block. Here's the key. Here we go, folks. Look, when I pulled the 5 kilogram block up so it was pointing straight, the force of gravity from the 5 kilogram block moved as well. Very important. There's the big idea. Okay? Notice what the force did. It moved. It rotated just like the block did. Okay? That's your key. Big step. Step number 2, put a big star by it. Make a note. You got to rotate the blocks and the forces. Okay? All right, let's go step number 3. FBD, the whole system. So, I'm going to go down here. We'll extend the page. And let me make sure I get a good color here. We'll go back to the black one. Now check it out. There's my FBD of both blocks. Okay, remember what my system is. My system is still everything together. Okay, let's put our forces on it. We have the force of gravity from the 10 kilogram block. We have the normal force from the 10 kilogram block, and we have the force of gravity from the 5 kilogram block. All right? So the question is, Let's do F equals ma now. Okay. I'll change to blue. Now, we're going to do sum of the forces equals m times a. Now, in the y direction, the normal force and the force of gravity are going to balance because that 10 kilogram block is not moving up and down. So let's just do it in the x direction. And all we have, we sum the forces. And what are they? Force of gravity from the 5 kilogram block equals m times a. Force of gravity from the 5 kilogram block is going to be 5 times gravity is 10. And what's the mass? Well, we got to be careful. It's the 5, but we're also accelerating the 10 kilogram block too, and that equals A. Very important. Did you see what I did again? The mass is everything that's being accelerated. That's where kids have trouble. So on the left-hand side, we have 50, and we're going to divide that by 15, and that's going to equal A. Now, I'm not going to do the math. I don't have a calculator with me right now. Okay? There's our acceleration. Now, we got to go back a step. We just found A for the whole system. That's number 4. Now, we have to start back over and do an FBD and Newton's second law for just one individual block. Okay, so let's move down again. And I'm going to extend the page, and I'm going to draw a line right over here. Okay, now let's FBD just one of the blocks. Doesn't matter which one. Let's choose the 10 kilogram block. Let's choose the 5 kilogram block. It doesn't matter. So in the 5 kilogram block, what forces do we have? I chose the 5 because there's fewer forces on it. We have the force due to gravity from the 5 kilogram block. And then what's the other force on that? On just that block? It is the force of tension. So do F equals ma on it again. All right? Change over to blue. I didn't change over to blue. Sorry about that. Change over to blue. And hope I did it this time. The sum of the forces equals m times a. Now, up here, 5 kilogram block only. I'm just having a terrible time with this pen today. I apologize. All right. So what are some of the forces in the y direction? Force of tension minus, whoops, let's do this. Force of tension, let's make down positive. Do you want to make down positive or up positive? What do we usually do? I'm trying to remember. Let's make up positive. So let's do the force of tension minus force of gravity from the 5 kilogram block equals m times a. Now, trying to find force of tension. Let's plug in what we have. Force of tension minus 5 times 10, that's m times g, equals the mass, which is 5. And how much is it accelerating? It's accelerating 50 divided by, 15. All right, now all we have to do is solve. Can you see we just solved for the force of tension? There we go. All righty. So basically the big idea is this. We solve these problems by doing the entire system, all the blocks and the ropes together, and then what we do is we pick one of them and use the acceleration we found to find the tension. All right, sorry about taking so long. That was awfully long. Here's your video lecture problem. Hope you enjoy.